Hello dear audiences, welcome to episode 17 of Probability and Statistics for Engineers. I am Mohammad Momezadeh, the presenter of this lecture. Previously we discussed about several types of the discrete distribution. About the binomial and multinomial distribution we were discussed. So in this lecture we continue our discussion by talking about another type of the distribution, discrete distribution especially. So you can see the topics in the next slide. Over here we have hypergeometric probability distribution and geometric distribution. And if we find the time for remain part, we will discuss about the Poisson distribution as well. And in the meantime, we will discuss about the approximation for that type of the distributions. Indeed, some of the distribution can be approximated or estimated with another one, and we will discuss about them as well. Let us start to discuss about the hypergeometric distribution function. So over here you can see the definition for hypergeometric distribution. The hypergeometric distribution is described by three parameters: the capital N, the total number of objects, K, the number of objects of the first type, and small n, the number of objects to be chosen. The probability distribution of hypergeometric random variable x is defined as follows. So you can see the formula for that type of the distribution, and also the variance and the mean of this distribution is given over here. So let us take a look on that definition and theorem precisely. So the best example for that distribution can be considered by using a bowl or the bag that contains some marbles or the balls. So if you just consider a bag, let me just sketch a bag over here that contains several balls or marbles. For instance, we have four orange balls over here, and also let us put the another color as well, the purple one, three purple one, for example. So over here we can draw the balls without the replacement. The points over here is about the replacement or without the replacement. So we just draw, for instance, three balls from the resources that we have it, or from the bag that we have it over here. Right now we have something that we should mention it. First of all, the number of the balls inside of that bag. So we have 3, 4, 5, 6, 7 balls totally in a bag. Let us denote that number by capital N, and the capital N is 7. And of course we have 4 of them as a orange and 3 of them as a purple, and we draw indeed 3 of them from the bags. When the replacement is not allowed, means that we didn't replace it back over the bag, so the probability of choosing for example the orange ball from the second one to the third one, that probability is changed, and it's not constant or invariant through the different drawn over there, because the replacement is not allowed, and because of that the probability is changed. For example, if I draw the first ball, then based on a ball that I drawn it, if it's purple or it's orange, the probability of getting orange for the second one will be changed. So if I denote the x, the random variable, as a number of orange ball, for example, let me just mention it over here. X denotes over here the number, denotes the numbers of orange ball over there, orange balls. So I have some distribution for x. Let us calculate that distribution by using the knowledge of the previous parts that we have it. So the x, or the number of that orange ball, can be calculated as follows. Means that we should construct a table with 2 rows indeed, and in the first row we should mention the value of x or a random variable. So this x or xi can be assigned with the following numerical values. It can be 0, it can be 1, it can be 2, or it can be 3, because maximum we can have 3 orange balls inside of the drawn balls that we have it over there. And the second line should determine the probability distribution function, or the probability of getting that balls. Let us calculate the x equal to 0 to see that how can we calculate it. So indeed, for f of x at the point 0 means that we have no orange ball inside of it, or I can rewrite that one by the following expression. I can rewrite it as a probability of a number of the orange ball is equal to 0. So probability of x equal to 0 should be calculated. So this one is equal to, let me just put one line, one fraction. At the denominator of the fraction, I should write all possible outcomes, or the number of the cases that we can consider it over here. Since we have 7 cases totally, then we should draw 3 balls out of these 7 balls. Means that 3 out of 7 is a total cases that we can consider it over here. And because we just drawn the balls without the replacement, and it's a group of balls that we drawn it from the back, so we should use the combination. So the denominator should be considered as a combination of 3 chosen out of 7. So what about the numerator? Because we choose 0 balls, or the number of the orange ball is 0 ball out of the number of the orange balls, which is 4. So we choose 0 out of 4. And also we should choose the remained parts, the remained balls, which is 3 out of the number of the purple balls, which is 3. So the numerator of this fraction is equal to 1, as you can see, and the denominator of that one is a 7 times 6 times 5. It will be happen because of that calculation, and if you just calculate it at the end of the day, it will be 35. So we have 1 over 35. Then the probability over here is 1 over 35. Let us calculate for x equal to 1 to see that what do we have if x is equal to 1, and later on we will get the general formula, and then we can actually recap the discussion to return back to the hypergeometric distribution. So f at the point 1, let us calculate f at the point 1, means that I'm looking for having only 1 orange balls. What is the probability of getting 1 orange balls out of 3 drowns from that bag? That's a case that we should evaluate it over here. The denominator will be as the same, means that the denominator should be the combination of 3 out of 7. Let me just rewrite it over here, 3 out of 7. And also for the numerator, I should choose 1 orange ball out of 4 cases that we have it, and the remains of the balls, which is equal to 2, should be chosen out of 3. So right now the numerator is changed, and we have indeed 12 over 35 for this case. So this calculation give us some insight about the calculating the general formula. We can calculate the case for the probability of x equal to 2 and x equal to 3. But let us take a look if we want to calculate the probability distribution function at the point x, arbitrary value for the x. I mean that if I want to know what is the probability of x equal to the capital X, uppercase X is equal to lowercase x, we want to know that what is that formula. The denominator should be equal to 35, or it's equal to 3 out of 7, because totally we choose 3 drawn out of 7 bags in a total that we have it over there. But the numerator should be calculated as follows. We need x balls, x orange balls, and this x orange ball should be chosen out of the resource of the orange ball over there, which is equal to 4. So is x out of 4, x chosen out of 4 cases, and the remained cases, because we have 3 cases in total, the remains will be 3 minus x, and this one should be chosen out of the second kind of the balls that we have it, which is equal to 3. So 3 minus x out of 3. And this value should be calculated as a general formula. But this general formula gives us the information about the hypergeometric distribution indeed. This type of the random variable follow the hypergeometric distribution. And as you can see, if we denote the number of the resources as n equal to 7 and number of the drawn cases by the small n, let me just use the lowercase n for the number of the drawn cases, and also we can denote the number, divide or split the resources to 2 parts. One part contains the cases that is in our concern, and the another one is not in our concern. So let me just shift that purple balls to the top, then I can split them by sketching a line over here. Number of the cases that we concern about it are the orange balls, and let me just put k to denote the number of the orange balls, means that k over here is equal to 4. Let me just put a number for n as well, which is equal to 3, which determine the drawn balls from the resources that we have it. So right now the remained parts, or the purple balls over here, is the total, means that the capital N minus k, which is equal to 7 minus 4 or equal to 3. So right now I just denote all the elements or character of the hypergeometric distribution over here, and we can rewrite our formula by using that things. Means that if I just rewrite that formula, you can see this formula over here. Means that at the denominator we choose n, small n number of the balls out of the capital N or the uppercase N of the resources. For the numerator, I choose x cases out of the favorite part of the resource, means that x should be chosen out of k. And the remained one means that the remained cases, the remained balls are n, the total balls that we drawn it, minus x, out of the second kind, and the second kind is denoted by capital N minus k. So in this case you can see the formula of the hypergeometric distribution. Let us recap all this information and rewrite the hypergeometric distribution again over here. Let me just do that one here. So let us gather all the information that we had it from very beginning. First of all, we had a resource of the elements or the objects, and I just sketch it with the bag or the ball over here. So that objects are capital N. So we have capital N numbers of the objects that we should consider in this example or in this situation. So we split the resource to 2 parts. K of them are favorite, and we put it over here, and the remaining parts will be capital N minus k. So I split the resource to 2 parts. One of them contains k objects that are our favor, and the another one is not our concern, that we have n minus k number of them. So from this resource we draw a group of the elements or the objects. So this group of the objects or elements drawn from that resource, let us put it over here by some balls to determine that object. So for sure we have n, the small n numbers of the object that is drawn from the resource. Over here the important part is about the draw the objects from the resource without replacement. Because of that, the probability of choosing the favorite one, choosing the selected one, the success over here is changed from one object to the another one. So if the replacement has been done, then this type of the distribution will be the binomial distribution. I hope that you understand this actually tricky things inside of this question. Indeed, if the replacement is happened, this n drawn looks like terrials, and they are independent from each other if the replacement is happened. And then we can discuss about the cases over here again for each of that actually balls or objects that we draw from the bags. We have two cases. One is our favor, that we can denote it by success, and the another one is not in our favor, that we can put it as a failure. And if the replacement is happened, the probability of success and failure will be constant or persistent through that type of the draws, and then you have the binomial distribution. However, over here in this type of the distribution, because the replacement is not happen, then the probability of belonging to the favor cases for the first ball is different from the second one and the third one and so on. So it means that we have the resource of capital N numbers. We split it to two parts, the k and n minus k, and we draw the small n. As I said it before, if x denotes the number of the favors balls or the successes over here, so it over here x denotes the number of objects from the favor part. So over here, if the replacement is happen, simply you can consider it as a binomial distribution. Again, I should mention it over here. If the n objects is considered over here, let me just put that sequence of the objects at the right side and rewrite it again. If we have n objects and also the drawn of that one, the replacement is allowed, we do it with replacement, then it's changed the question totally. It's changed everything totally. Why it's gonna be changed? Because over here, then for each of these cases, each of these objects, we have two situations, like a success and failure that we had it in a binomial distribution. And of course, the probability of the success over here can be calculated as a number of the favors, means that the k over the capital N, which is the total cases over there, and the Q, or the probability of a failure, will be equal to the number of the failure cases or not favor one, which is the capital N minus K over N. And as you can see, the addition of P and Q is equal to 1. If it's happened like this and replacement is happened, then X follow the binomial distribution with the number of the trial as a n, and also the probability of the success as a k over n. And it's very simple to see that in this case you can say that the probability function, the probability distribution function over here for the value of x can be calculated simply by the methods that we had it. I mean, it's going to be x out of n, x out of the n cases, and the probability of the success is k over n, the capital N to the power of x, the number of the success over here, and the probability of a failure means that n minus k over n, the capital N indeed, n minus k over the capital N to the power of the remained cases, which is n minus x. But over here, the replacement is not happened. We just discussed about the situation without replacement. That's a question that you may have it in your mind about this situation. It means that it looks like a binomial distribution with one difference over here, that the probability of a success and failure is changed for that type of the terreals, and that terreals are not independent over there. So means that, let me just erase that one and talk about the situation that we have it. So over here we don't have any replacement, means that we take them out, we draw them out without replacement, and this lead us to this type of the distribution, means that then the distribution over here, the distribution function over here will be as follow. So it will be a type of the fraction. At the denominator of this fraction we have indeed cases. All cases, we should put all the points in the sample space, because we draw n number of the objects out of capital N resources. So at the denominator we choose the small n out of the capital N. So this is the all cases that we have it. Then at the numerator you should choose the number of the favor cases out of the resources of a favors, which is equal to k. So x should be choose out of k, and the remained cases, which is n minus x, the small n minus x, should be chosen out of the number of non-favor cases, means that the capital N minus k. So with that discussion you can find the similarity of this distribution and binomial distribution. For the binomial distribution, if you remember that the expected value of the binomial distribution was equal to n times p. So it was equal to n times p, and determine the number of the terreals, p determine the probability of the successes. So over here we should follow the same thing. To memorize it better, you can do the same thing, means that you should remove p, and instead of the p you should put the value that you have it for the p over here, means that k over the capital N. So this will be the expected value. However, by calculating the expected value from the formula you can reach to the same thing, but the variances is a bit different. So for the variance of x, you remember that the variances of x for the actually binomial distribution was equal to n times p times q. So means that, let me just replace it back, the p over there. So we have n times p times q. So over here we should replace p and q by the corresponding value that we have it over there, means that instead of p I should write k over n, and instead of the q you should write n minus k over n minus k. What do I mean? Okay, so the favorite cases, the probability of favorite cases is k over n. The probability of actually non-favorite cases, the cases that is not our concern, will be the capital N minus k over capital N. So but in this case it's not enough to do that things, we need one more terms that we should replace it over there. So that term is a correction coefficient. Indeed, we call that one as a correction coefficient, the capital N minus n over the capital N minus 1. So you should replace over there the value like this, and then you will have that theorem. So this part is called the correction coefficient. So let me just write it over here, that we denote this part as a correction coefficient. So this correction coefficient helps us to calculate the variances, means that you don't need to memorize anything else. The probability distribution is clear based on this definition. If you just keep it in your mind, this structure that we have the capital N objects of the resources, and we draw the small n out of this resource, and the resource is split to two parts, the k objects in a favor part and capital N minus k objects in non-favor part, and x denotes the number of favor objects inside of n round. Then the distribution function for that x, for that random variable, is equal to this expression, and for expected value and the variances we have n times p again, and instead of p you should put k over capital N. For the variances we have NPQ times the correction coefficient. Why do we call to this one the correction coefficient? That may be considered as your question. But over here, take a look at the cases that we have it. So if N is too big in comparison with a small n, then what's happened? Indeed, if n is too big in comparison with n, means that this probability which is changed from one object to the another one is not changed that much anymore. So if you just take a look over here, the probability of getting the first one is k over capital N, and if the capital N is too big, by removing one object from the k cases of a favor and the capital N, then the probability of the success for the second one will be not changed that much, and the attitude of this distribution will be clearly close to the attitude of a binomial distribution. And if you just compare it over there, you can see that, for example, if we have 1,000 cases in our resources and we remove only 3 cases from there, then the capital N minus n will be 1,000 minus 3 divided by 1,000 minus 1, and this value is totally close to 1. I mean, you can consider it approximately equal to 1, and for this reason this correction coefficient just help us to correct the variances and calculate the variance as well. Let us take a look at the variance again over here. So as you can see, the theorem over here, we have the similar things that we talk about it. So the mu, or expected value, is nk over the capital N, which is as the same as n times p. By comparison, the cases that we have it, we have for the variances the correction coefficient n times p times q, and you can see the value. If you just take a common divisor, the capital N, you will reach to the same formula that we have it over here. So this is the hypergeometric distribution, and I hope that you understand the differences between the hypergeometric distribution and binomial distribution. Over here at the hypergeometric distribution, the probability of each terial will be changed based on the location of that terials indeed. But at the binomial distribution, the probability of success and failure is constant. So let us take a look at the next example. So at this example, a random committee of size 3 is selected from 4 doctors and 2 nurses. So it's better to determine the resource of elements that we have it over here by one bag and put 4 doctors over there. So let me just put 4 doctors over here, and also 2 nurses that we have it in our resources of the elements or the objects nurses. Let me just put NU to determine the nurses. So by the other words, our resource can be split to 2 parts. One part the doctors and the another one the nurses. So when you just read the question, it's better that you describe the situation for yourself by some symbols. In this way you can determine the type of the distribution easier than the another method. So the size of this committee is size 3, means that we selected 3 persons out of this resource that we have it over here. So we have 3 persons, let me just put 3 persons that we draw from that resource, and this determine the number of the committee, the size of the committee that we have it. So 3 persons are selected out of them, and it's important to consider this word. We have a committee. When we have a committee, means that it's a group of people and the replacement is not allowed. Means that if, for instance, we have one specific person like Dr. K, for example, inside of that resource, then Dr. K cannot be repeatedly chosen out from that resource and be in a committee. Another person should be chosen after that you choose Dr. K. So it means that the person over here cannot be repeated, so the replacement or return them back and again choose them is not allowed over there. However, if the replacement is allowed, then the type of the distribution should be changed. And the important things over there is the x, or the random variable. Over here they said that to find a formula for probability distribution of random variable x representing the number of doctors on the committee. So x denotes the number of doctors in that committee. So it's important to mention it over here as well. Denotes the number of doctors on the committee. So it means that the favorite part of the resource is a part at the top. So you may use the alphabet or that type of the label which we use it for the hypergeometric distribution. Means that you can put k for that one, n minus k over here determined by two cases. The capital N is a number of the total cases, and the number of the chosen people is a small n. Right now you can write the distribution function. So as you remember from the previous slide, the probability of capital X, or the number of the doctors, is equal to the small x. Can be denoted by the value of a probability distribution function at the point x, and it's equal to, so let us rewrite that formula again. We should sketch one fraction first, one straight line. At the denominator, the number of the element that we choose it over here is 3% out of the total, which is 6, so we just choose 3 out of 6. And then the x, the number of the doctors, should be chosen out of the resource of the doctors that contains 4 elements, and the remained cases, which is 3 minus x, should be chosen out of the resources of nurses, means that out of 2. And this x over here can be calculated for the value of 0, 1, 2, and 3, because that committee could contains only the doctors, and we have 0, 1, 2, 3 as a restricted value for the x over there, as a allowed value over there. So this gonna be the distribution function. At the second part of the question, they ask you to find the probability of x between 2 and 3. X will be between 2 and 3. So this contains two probability. Indeed, it's equal to the probability of x equal to 2. The number 2 is there, and also the number 3 as well. It's number 2 and number 3, because the equality is there, and the number 2 and 3, both of them should be considered as a value of that one. So it only needs to replace number 2 and 3 in the given fraction. Means that again we have 3 out of 6, 3 chosen out of 6 cases at the denominator, then 2 out of 4 2 out of 4, the remained parts which is 1 out of 2 should be written over there, plus again 3 out of 6 at the denominator, 3 out of 6 at the denominator, and also the number of the elements is 3 out of 4, the number of the doctors, and the remained one means that 0 should be chosen out of 2 cases. And you can calculate that value easily by multiplication, multiplying the values, the corresponding value. So it will be 20 at the denominator. Over here we can calculate it. So the value will be 0.2 if you just calculate that things. Of course, you remember how to calculate that type of the permutation combinations over here. For instance, let me just calculate 3 out of 6 and write it over there. That how can we calculate it? 3 out of 6 means that we have 6 factorial over 3 factorial over 3 factorial. So we have this expression. after that you want to calculate that one, you can cancel the given terms one by one. You have 6 times 5 times 4 times 3 times 2 times 1. So this is the expression that we have it at the numerator. And at the denominator we have 2 times of 3 factorial, and 2 times of 3 factorial means that we have 3 times 2 times 1 indeed. So if we just put it over here, the value, so we have 3 times 2 times 1 and 1 more times for that case indeed. So let me just put it here. So right now you can cancel the given expression by this relations. So as you can see, this 3 and 3 will be cancelled, 2 as well with the 2. 1 is okay, you don't need to cancel it, but let me just cancel it as well. 3 times 2 also cancel with that 6. The remaining one is 5 times 4, which is 20. So the denominator of both of them will be 20. So you can do the same thing for the remaining parts as well. Let us take a look at another example. So I designed the next example such that you can find the binomial, multinomial, and hypergeometric distribution in one question. And you may find this example interesting. So let us take a look at the situation that we have. There is a ball, there is a bag that contains the following balls, means that it contains 4 orange balls, 4 blue balls, and 3 green balls. And we draw 3 balls from that bag. In the question said that if x denotes the number of blue balls, then without replacement and with replacement find the distribution function for the given x. So first of all, if the replacement is not allowed, means that we didn't return them back over there and draw it again and do that time severally. So means that the probability is changed one by one from the first ball to the second one and for the third one. I mean that one is not constant. So this type of the case is determined by hypergeometric distribution, as we said it before. So for the part A, you should calculate the distribution function by using the hypergeometric distribution, means that the probability of x will be as follows. Since that we choose 3 balls out of 10 cases that we have it, the denominator will be 3 chosen out of 10, because we have 10 balls inside of the bag and we choose 3 of them out. And the number of the favorite cases over here is x, because it's a blue balls over there. The favorite balls part is blue balls, or the k over here, it should be 4. This is 4 balls over there, so x should be chosen out of 4, and the remained one means that 3 minus x should be selected out of 6 cases which is remained over there. It doesn't matter that we have 3 colors over there. The important thing is our favor, and it's not our favor. You should take a look at the cases that we have it, which can be splitted to the favorite part and not favorite part. So of course x can be equal to 0, 1, 2, or 3. This is the distribution function if the replacement is not allowed. So if the replacement is happen, then the situation is changed totally, and we have the different cases. So, but let us take a look at the second case, when the replacement is allowed and one by one they replace it back, and we calculate the probability on that case. So if the replacement is allowed, then the situation is changed, and for these 3 trials, then we have 2 cases for each of them. If I just consider it over here and write it and sketch it again over here, you can see that for each of them we have 2 cases. One case is that the given balls will be blue, then we call that case as a success, and this success has a probability of 4 over 10, because we have 4 cases of the blue out of 10 cases, 4 out of 10. And we have the another case of a failure that the given ball, the draw ball, is not blue. So then the Q, the probability of failure, will be equal to 6/10. And because the replacement is happen over here, means that for each of them, this probability is as the same, is not changed for the second and third one. So for the second and third one also, the probability will remains a constant value. It will be 4/10, the probability of choosing that one. So the distribution will be changed, and we have a binomial distribution right now. So f of x over here, or the distribution function for getting the blue balls, or for that random variable, will be the selected of x out of 3 cases, then multiplied by the probability of the success, which is 4/10, or 0.4, to the power of number of the successes, which is x, times the probability of failure, which is 0.6, multiplied by n minus x, or 3 minus x over here. So 3 minus x over here. So this is the part B of that question. As you can see, with one phrase over here, the distribution is totally changed. For the part C, they ask you that what is the probability of getting one from each color with replacement. Right now, if we consider the x1, so we should define the another random variable x1 of number of, if x1 determine number of the green balls, for example, number of green balls in our draw. So if I consider x1 as a number of green balls over there, x2 as a number of actually orange ball, means that everything is as the same orange ball over here, just the color is changed to the orange. And the x3, the last random variable over here, determine the number of the blue balls, for example. You can choose any of them. Then this type of the question, I mean the part C, asks you to find the probability of getting x1 as 1 ball, x2 as 1, x2 as 1, and x3 also is equal to 1. And the total number of the objects that we have it is equal to 3. N is equal to 3. It's an addition of this 3 1 that we have it over here. It means that we can put 3 as a total number of the drawn over there. So it will be equal to, you should use them actually multinomial distribution over here, because we have 3 cases for each balls. We can consider it for the blue, green, or the orange. However, at the previous section, as a previous part also, we could have the green, orange, and blue, but we split the situation to 2 parts of the favor and not favor case. We could do that one, but over here the colors are distinguished, and we want to have exactly 1 cases of the green, 1 cases of orange, and 1 case of the blue out of the 3 cases that we have it. Then we should multiply it by the probability of each of them. Means that the probability of getting green is 0.3. The probability of getting actually orange will be 0.4, and the probability of getting blue as well is 0.4. Actually, we could calculate the situation by using the multiplicative rule as well. As you can see over here, it will be 3 factorial over 1 factorial over 1 factorial. This one, actually, we don't need to repeat it again. So this part is 3 factorial over 1 factorial, 1 factorial, 1 factorial. So indeed, we have 3 factorial of the permutation between these 3 elements, and you can use the multiplicative rule as well to calculate it without using any distribution. If you want it, you can evaluate the probability of part C without any distribution, and just use the multiplicative rule, but you should keep it in your mind that the order of the colors 3 factorial will be changed, means that you should calculate the probability of all cases. Don't forget to do that one, means that the probability of orange green blue or green orange blue or blue green orange, all of these cases, all these 3 permutation should be calculated. And of course, because they are independent and the replacement is allowed, so you can multiply their probability as their intersection of their probabilities. So I will finish our lecture with this example, and I hope that you understand the differences between the binomial distribution, hypergeometric distribution, and multinomial distribution by using this type of the example. As I said it before, it's important to diagnose the type of the distribution. The remaining parts is too easy. I mean, you can solve it by just replacing the number instead of the variables inside of the given formula. If you know the correct distribution, then solving the question is too easy. Thank you for your attending.